Okay, so now let's see how to solve the recurrence relations. We have here x of n is x of n minus 1 plus 5 for n greater than 1, and x of 1 is 0. So x of n is x of n minus 1 plus 5. So I'm going to do kind of like an induction approach. So x of n minus 1, from this is x of n minus 2 plus 5. So I'm substituting for x of n minus 1 based on this as x of n minus 2 plus 5, then this plus 5 comes in. So it is x of n minus 2 plus 2 times 5, or 5 times 2. So now I can substitute for x of n minus 2, x of n minus 3 plus 5, and again 2 times 5, so it is 3 times 5. So I can keep writing like this. So x of n is x of n minus I plus I times 5, right? So we can go until we can replace this with 1. So if x of n minus I equals 1, then n minus I equals 1, then I equals n minus 1, right? So n minus I equals 1, so I equals n minus 1. So I can replace I with n minus 1, so it is x of 1 plus 5 times n minus 1, so that is x of 1 is 0, so it's 5 times n minus 1 instead of n. Then x of n is 3 times x of n minus 1 for n greater than 1, and x of 1 is 4. So x of n is 3 times x of n minus 1. Then x of n minus 1, I can write it as 3 times x of n minus 2. So it is 3 times 3 of x of n minus 2. So it is 3 square x of n minus 2. Then x of n minus 2 is 3 times x of n minus 3. So it is 3 square times 3 times x of n minus 3. It is 3 cube times x of n minus 3. So it is, in general, x of n is 3 to the power I, x of n minus I. So again I can set I equals n minus 1. So it is 3 times 3 to the n minus 1 times x of 1, which is 4. 4 times 3 to the n minus 1, I can say it is 4 over 3 times 3 to the n. So it is theta of 3 to the n. Okay. Now x of n is x of n minus 1 plus n for n greater than 0, x of 0 equals 0. So x of n is x of n minus 1 plus n. Now I can replace x of n minus 1 with x of n minus 2 plus n minus 1. So it's x of n minus 2 plus n minus 1 plus n. Now x of n minus 2 can be replaced with x of n minus 3 plus n minus 2. So it's x of n minus 3 plus n minus 2 plus n minus 1 plus n. So I can keep on doing that. So it is x of n minus I plus x of n minus, this is like I minus 1. So this is n of n minus I plus 1. So it's something like this. Right, x of n minus I plus, this is I, right? So 3, then 3 minus 1. So I can write it similarly. This is x of n minus this plus then x of, sorry, there's no x here. Okay, that's n minus I minus 2 and so on. Okay, plus up to n. So this is n minus I plus 1, that's what we have here, then n minus I plus 2, so on up to n. So now I want to put here, this is 0, so I want to make this as 0, so I put I equals n. So this is 0, x of 0 plus I equals n means it is 1, then this is 2, 1 plus 2 plus up to n. So x of 0 is 0, so it's 1 plus 2 plus up to n, which is n times n plus 1 over 2, which is theta of n square. Okay. Alright, so now x of n equals this. So when you're given like n over 2, we have to use n equals to the k approach. So x of 2 to the k is x of 2 to the k minus 1. When I substitute n equals 2 to the k, we get x of 2 to the k minus 1 plus 2 to the k. And now I can substitute for x of 2 to the k minus 1, x of 2 to the k minus 2 plus 2 to the k minus 1 plus this 2 to the k as it is. So it is x of 2 to the k minus 2 plus 2 to the k minus 1 plus 2 to the k. So again I can substitute for x of 2 to the k minus 2 as x of 2 to the k minus 3 plus 2 to the k minus 2. You see here 2 to the k, 2 to the k, 2 to the k minus 1 is for x. So this is x of 2 to the k minus 2 is x of 2 to the k minus 3 plus 2 to the k minus 2. Okay, so I can keep on doing that. So it is x of 2 to the k minus I plus again like see 3, then 3 minus 1, 3 minus 2, like that. X of 2 to the k minus I plus 2 to the k minus I minus 1 with parentheses inside. But I can say that is k minus I plus 1, then I plus 2 and so on. So now I want to get this as 1, right, 2 to the k minus I. So if I put I equals k, I can get 2 to the 0. 2 to the raised to 0 is 1, right? So if I put I equals 0, I get, so if I put I equals k, I get x of 2 to the k minus k, which is 2 to the 0, which is 1, plus if I put I equals k, here is 2 to the k minus k plus 1 to 2 to the 1, 2 to the 2 and so on up to 2 to the k. And this is x of 0, so x of 2 to the 0, which is x of 1 is 1, so 1 plus 2 to the 1 plus 2 square root to the k is 2 to the k plus 1 minus 1 divided by 2 minus 1, but 2 minus 1 is 1, so it is that of 2 to the k, and I can replace that as 2 to the k is n, right? So I can say it is that of n. Okay. So same thing with n equals 3 to the k here. Okay, so x of n equals x of n over 3 plus 1. So I put n equals 3 to the k. So I can say this is x of 3 to the k is x of 3 to the k minus 1 plus 1, because it's n over 3, so 3 to the k minus 1 plus 1. So now x of 3 to the k minus 1 is again from this x of 3 to the k minus 2 plus 1, and this plus 1 comes as it is. So it's x of 3 to the k minus 2 plus 2. Then x of 3 to the k minus 2 is x of 3 to the k minus 3 plus 1. Then plus 2 is already there, so it's x of 3 to the k minus 3 plus 3. And we can go up to like x of 3 to the k minus I plus I. Now if I put again I equals k, 3 to the k minus k is going to be 3 to the 0, which is 1. So if I put I equals k, it is x of 3 to the k minus k plus k. So it is 1 x of 1, which is 1. So it's 1 plus k, which is k, that of k, right? So if I now replace k with log n to the base 3, because you see here if n equals 3 to the k, k is log n to the base 3. Okay, so that is 1 plus log n to the base 3, which is nothing but that of log n. So same thing with the number of bits needed for the binary representation of n. So if n equals 1, you need 1 bit. If n equals 2 or 3, 2 means what? 1 0, 3 means 1 1, so you need 2 bits. Then 4 to 7, right? 1 0 0, 1 0 1, and all these things, you need 3 bits. Then 8 to 15, you need 4 bits, and so on. So you see here the range doubles, right? 1 and then 2 to 3 2 integers, and 4 to 7 is 4 integers, then 8 to 15 is 8 integers, then 16 to 31 is 16 integers, 32 to 63 is 32 integers, and so on. So as you increase the number of bits by 1, the range doubles. right? So if I want to find the number of bits needed for say 32, it's nothing but the number of bits needed for 16 plus 1, essentially, right? So whatever the basic operation here we do, let's say you see here you do one division here plus 1, so there's an addition, this is division, so we can take, and both of them are done once, so the number of divisions is 1, number of additions is 1, one time for each recursion. So we can compute the complexity for either one of them. So we'll do for addition. The number of additions you need to do to compute a of n is number of additions you need to compute to do a of n over 2 the floor plus 1. Okay, so for example, if you want to find the number of additions you need to compute the binary number of bits needed for 32, you would, whatever is the number of additions you need to compute the binary representation of 16 plus one more addition. Okay, so it's like 5 bits then plus one more addition, that's 26 bits. So this is now again to the n. Now if your n is 1, you don't need any addition, so a of 1 is 0. So now we need to transform this to the n equals to the k, 2 to the k form. So if I do that, it's a of 2 to the k equals a of 2 to the k minus 1 plus 1 for k greater than 0. Why? Because you have here 1, right? So 2 to the 0. So if k is 0, a of 2 to the 0 is 0. So that's why this one recursion holds for k greater than 0. Okay, so now I can do the same kind of recursive analysis, and then you'll get like this. So this is 0, a of 2 to the k minus k is 2 to the 0, which is 1, but a of 1 is 0 for us, right? So 0 plus k, which is theta of k, which is theta of log n. Okay, now the factorial. So we know n factorial is 1 times 2 times up to n minus 1 times n, right? So but this one can be written as n minus 1 factorial, right, times n. So factorial of n is factorial of n minus 1 times n. So whatever is the basic operation, which is multiplication here, is the number of multiplications we do is the number of multiplications to compute factorial of n minus 1 plus one more multiplication. Okay, and if you want to compute the factorial of 0, which is 1, you don't need any multiplication, so m of 0 is 0. Okay, so for any n greater than 0, m of n is m of n minus 1 plus 1. One more multiplication. Then what was here to find n minus 1 factorial? So we can simply solve like this. M of n minus 1 is m of n minus 2 plus 1. So m of n is m of n minus 2 plus 1 plus 1. So that's m of n minus 2 plus 2. Similarly, m of n minus 2 is m of n minus 3 plus 1. And it is m of, if you substitute for m of n minus 2 here, m of n minus 3 plus 1, then plus 2, this plus 2, so it's m of n minus 3 plus 3. You can keep on doing that until you get, say, if you put 0, n here, n minus n, you'll get m of 0, which is 0 plus n, so it's going to be theta of n. Okay. Stop with this.